Welcome. In This is lesson 2 in the module of dimensional analysis, and in lesson 2 you will learn about pi theorem. So this lesson has 3 parts. So that will be the first part. So in the first part we will learn about physical model, the principle of similarity, and how pi theorem connect these two together. So what you will learn in this video is that you will learn the purpose and different types of physical model. You will understand the principle of similarity in dimensional analysis, like the similarity between a physical model. So physical models, that's basically a replica of an object or a system. So you create like a physical model for it, and it's an actual physical model. It's not a numerical model in a computer, but like it's an actual model with a different dimension, whether like larger or smaller or whatever. And you need to maintain certain similarity between your prototype, like your original system, and your model. That's mainly geometric similarity, kinematic similarity, and dynamic similarity, so that you can, whatever you learn from your physical model, like the small scale one, or you can uh, rescale it, like you can do some rescaling to the original model. So basically what you learn something about from the physical model, and this will be applicable to the original model through some scaling principles that we will understand. That's the principle of similarity. And then we will see pi theorem, how pi theorem is important, like in conducting these type of analysis, basically. Yeah. So let's start. So like a physical model, as I mentioned, that would be like a replica of of an object or a real system. And there are different types of physical model. We've seen already one, like fundamental model, like in the previous lesson. I showed you like Darcy experiment where he had like where Darcy conduct had this sand column, and you can use this sand column to learn about flow in porous media. So that is a fundamental model basically. So whatever you learn from this column, you can uh, infer or learn about some physics-based rules like Darcy law, for example. So that would be like an example of Darcy experiment to understand principle of flow in porous media. Another example here, like as you see in this picture, Hill-Chow model. So this model, so basically you can think of this as like an aquifer, and this is like two rivers. So you can think of this as an island, for example, that's surrounded by water or surrounded like by two rivers here. And from a model like this, you can learn also about like the law of physics. So you see here, for example, the flow is mainly vertical here because you have high energy here and low energy here. So if you see how water is flowing from high to low energy, but then start to become horizontal here. So you see vertical flow and then horizontal flow, and then the water will flow to here. So basically you can use a model like this for different purposes, educational purposes, to illustrate some uh, concept in fluid flows, but you can also use it for example, like to validate a numerical study. Yeah, so that would be another use. Like if you have a numerical models that you want to validate, for example, you can use like a model like this one. Yeah. Uh, Okay, so another type of physical model is flumes. So we use flumes a lot so as to study like stream flow and sediment transport. So we can study this with a numerical model, but sometimes see this is our real system and this is the physical model, the replica. So this is like we create this replica in the lab for our real system, and then we use it to study flow and sediment transport in that stream. And how could we, what we learned about this replica, scale it back to our real system? That, well, This is called like scale models, and that's why we need to do dimensional analysis and pi theorems. That's when they became handy and useful. Another type of physical model is like wind tunnels to test like for aircraft, bridges, vehicles, whatever. So we want to test like drag force, for example, yeah, for this aircraft. Yeah. So in these wind tunnel, like we will like in the next two videos, actually, I will show you like an example for one of these wind tunnel for testing. I think it's a bridge, like a column in a bridge, and you want to test the drag force on this column, and how could you scale from the your model, your physical model. So that's the physical model, and to the prototype, which would be the original aircraft, which will have a different dimensions as this one, like much larger than this one here. So this is called like the physical model. This is called like the prototype. Okay. And these are like example of models that are called like scale models. Yeah. Here, this is like another example of like structure model to evaluate structure behavior under loads and earthquakes. So the structure analysis, also physical models are used. So basically here you are making like a building and you want to study like like this is a giant shake table for earthquake resilience. You want to study like earthquake resilience and scale back to like your prototype, like your uh, uh, main building. Yeah. So that would be another other types other than the scaled like model, like fundamental model, like the RC law, or scaled models like these guys that you see here. There is also environmental and climate simulator. This is an example of Biosphere 2 at the University of Arizona. And basically, so Biosphere 1, that's the Earth. Biosphere 2, that is what you see here. And basically, you can use this to study changes in climate and other interaction like land and atmosphere interactions. Yeah. Okay. So these are example of physical models. So what we will be doing in these and next video, I will mainly focus on like scale models, like this guy and this guy and this guy, and I will show you like how pi theorem can be like useful uh, in analyzing these model and like to scale back from like your physical model to your prototype. So what you learn from your physical model, how you can scale it back and to learn something about like your prototype using pi theorem. Yeah. So let's start with before we do this, let's just start with the so to do this, like to do this scaling between your prototype, between your physical model and your prototype, these two things need to be similar. They don't need to be exact, not exact, like you see here in this image. These two are not exact, but they are similar. Yeah. So they need to be similar, not exact, but similar. And by similar, we means like basically three types of similarity. So first is the geometric similarity. The model must be the same shape of as a prototype, and so that you can just scale them with a constant scaling factor. So if you have the same shape, then you can scale it back to your prototype with a constant scaling factor. Second is a dynamic similarity, something that has to do with the velocity, which means that the velocity at any point in the model flow must be proportional to the velocity of the corresponding point in the prototype. So this is that would be called like kinematics similarity. So geometric similarities that has to do with length, kinematic similarity has to do with velocity, something that's changing in time. Yeah, how things are changing in time. Okay. And for to achieve the last type of similarity, which is a dynamic similarity, that has to do like with forces, you need to have kinematic similarity and geometric similarity. So basically, these two are necessary conditions for you to achieve dynamic similarity, which is the most restrictive similarity condition, and it's achieved like when all forces in the model scale by constant factor to corresponding forces in the prototype. So, and by the way, they don't need like all forces does not need like to scale one to one. But what is more important actually is not like the value, the magnitude of the force, but the relative importance of different forces like viscous forces, inertial forces. Like the relative importance of these forces need to scale uh, between like your model and your prototype. Yeah. Uh, so in summary, so that's like, let me show you this one. So in summary, uh, you need to achieve to have geometric similarity and kinematic similarity. That are the necessary condition to achieve dynamic similarity. Yeah. Like if you have these to achieve, that doesn't mean dynamic similarity is necessary achieved, but these are like two necessary conditions. Yeah. So, and we will look at this more like next video, how when we use pi theorem, how we can uh, ensure that we are achieving kinematic, geometric, kinematic, and dynamic similarity. Yeah. Okay. So let's look an example. Yeah. So we can look an example here. So like you consider like this is smooth cylinder, and that smooth cylinder could really be. It has like it could be like something like this in this bridge here. Could be in this like wind farm here, like in this wind mile here. And what we want to do, like we want to find like the drag force. Okay, so we want to find the drag force. So drag force, this is sometimes is referred to as like fluid resistant. It's the force opposite to the motion. So basically, like you have, like look at this boat, like you have the boat is moving in this direction. That's the thrust that moves the boat, the force that moves the boat forward, and the drag force that would be the force that is opposite in this direction. So here you have a drag force between solid and water. Here you have a drag force between air and uh, aero drag, the drag force between the solid and the air. And you can also have drag force between water and water or air and air. Yeah. So this is called like the drag force. So we want to study like a drag force. Let's say like you are designing this bridge and you want to understand like the drag force on this bridge. Yeah. So the drag force on this bridge, like so you have like water is flowing, so that will depend on what. So like you are just designing this experiment, like like you're working with your supervisor, and your supervisor told you, we are designing this bridge, and I want to see the drag force. I want you to go to the lab, conduct different experiment to estimate like the drag force, giving different factors. So what would be these factors that will affect the drag force? So of course, the most obvious factor, let me do this. Here's this one. Yeah, the most obvious factor would be, of course, like the shape of the factor. So let's assume that this is like a cylinder. So so the shape here would be circle. So that would depend on like the diameter of of that cylinder. So basically, as this diameter increase, you would expect like your drag force to increase. with it. Yeah. So that would be like one factor. I mean, what would be another factor? Like, of course, the most important and obvious factor is the velocity. Like, as the velocity increase, then your drag force will increase. So, like, you have like the velocity here. As the velocity increase, the drag force will increase. Yeah. What would be the other factors that will determine the drag force? The fluid itself. So, if this fluid is honey versus air versus water, then the drag force will be different. And if you remember from lesson one, for example, when we talked about fluid, like in Darcy experiment, we generally like represent the fluid by what? So like two important parameters that could describe your fluid. That would be like your uh, the density, and the other would be like the viscosity. So that would be like the density and the viscosity. Yeah. So basically, so it has to do with like the density and viscosity, so, and the velocity and the diameter. So that if you see here, now if I want to scale this, like what I'm conducting in my lab to the prototype here, like what I'm observing here in the real system versus like, so that would be like the real system here, for example, and that's what we conducting in the lab. Remember, uh, we have to achieve like a geometric similarity. So this guy should look to this guy with like with a scaling factor. So that would be like is smaller than this guy. Like this diameter here would be smaller than this guy. You need to achieve kinematic similarities that has to do with the velocity, and you need to achieve dynamic similarity, which has to do with mainly the forces, and forces has to do with mass, which are depending on the density, for example. Okay, so here, so we can say like the force drag, the drag force that's equal, that's a function of these things. Like the diameter, something that has to do with the geometry, velocity, something that has to do with the kinematics, and uh, density, something that has to do with the dynamics, and uh, viscosity. Viscosity, like, I mean, for example, density, uh, saline water is heavier, has higher density than fresh water, yeah? And same for the same volume, yes, heavier for the same volume than fresh water. Same like honey would be more viscous than water. Yeah? And the water would be more viscous than air. So that has to do with viscosity. Okay. Dimensional analysis can generate non-dimensional parameter to design experiment and report result. What does this mean? Well, I will show you this in a second, like to explain like this statement to you. Dimensional parameters, dimensional analysis can generate non-dimensional parameters. Non-dimensional parameters, we will see this, to design experiment and report results. So first of all, like what is this non-dimensional parameter? What do we mean? And then second, like how can we use dimensional analysis to find this non-dimensional parameter? And but more important, before like we know these two, like why this is important? Let me show you why this is important. So let's see here. Uh, so in this experiment, like this previous experiment that we talked about like a drag force, for designing this column or whatever, your supervisor told you, I want you to find like, I want to estimate like this drag force in the prototype based on like models, that physical models that you will create in a lab, and I want you to design this experiment for me, so we can, by changing different parameters. And remember, like here, our parameters, if you remember. So here's, this is a drag force. That is like a function of like different parameters. That's like a function of t, that's a function of velocity, that's a function of density, and that's a function of viscosity. So I want you to design these experiments. So I want like when I change like the diameter of the column, for example, I want to see how this will change the drag force. So you go to the lab, you design this experiment, you create like your column, you get some instruments that can measure like the drag force, and then you get like three different types of column. Let's say with different diameters, like 15 centimeters, 30 and 40 or whatever. So let's say you create 5 columns, and then water will flow, and then you will measure like for a given flow, you will measure. So for a given velocity, like let's say velocity 1, you will measure the drag force for each different diameter. So here, like this is diameter 1, let's say, I don't know, this is like 15 like centimeters, this is like 20 centimeter, 25 like centimeter, and so on. Yeah, so this is like here like different diameters. Yeah, and for each diameter, like a given velocity, you measure the drag force. Yeah, so you do this 5 experiments, and you think you are done. Uh, and like let's say each experiment will take like I don't know, a couple of hours or a day. Let's say a day. Yeah, so you spend a week doing this 5 experiments, yeah, and like making your measurements. Yeah. But then, like, you go to your supervisor and tell him, okay, this is like you change the diameter, that would be the drag force, yeah, for this physical model, yeah. But your supervisor will tell you, oh, you know what? I also want to see the impact of velocity, so I want you to repeat the same experiment, but like for different velocity. So, like maybe the velocity here is I don't know. 5 meter per like 1 meter per second or whatever. I want 1.2 and 1.5. Yeah, so you repeat the same experiment. So that's like you'll spend another week repeating the same experiments, like for the 5 different diameters that you have with a different velocity, and then maybe you want to try another velocity, then you spend another week. So like 3 weeks, yeah, to get the drag force now for different diameter and different velocities. Then you go to your supervisor and tell you, you know what, like this drag force is also a function of uh, what do you call this guy? Density. So I want you to try this with 4 different density. Yeah, like whatever you did here. So this like 1 week, 2 weeks, 3 week. I want you like you tried with fresh water, but now how about brackish water, and how about like saline water, and how about also like if we just want to do it with air. Yeah. So that's like 4 different dynasty. So again, okay, so now you did this. This will took like let's say 3 weeks, and you multiply by 4, so that's another 3 weeks, and you spend like what 12 weeks. Yeah. So you spend 12 weeks to study like different dynasties. So now for this one, like you will get another like 4 of these. Yeah, and then for this one, then you go to your supervisor and he tell you, you know what? I want also to study this at different air temperature. Like you did this just at like ambient air temperature, but I want to do this at different temperature. Like it's very hot, like ambient temperature, and it's very cold, and I want also I want you to study like different viscosity because it's a function of temperature. So again, that would be like 5 times 3 times 4 times 6. So that was like how many experiments? That's like 450 experiment. Yeah. So if each experiment take a day, that's like more than a year of work. And so that's not very smart. Yeah. Like spend 1 year of work like doing all this experiment, you'll get confused. And the problem is not how to do this experiment, the time it takes to do this experiment. The problem is how are you going to represent the results? You're going to have 540, like 5 times 3 times 4 times 6, that's 450. You'll have 450 of these graphs. So like you'll have 450 sheet, and then like your supervisor will tell you, okay, I need for this density and this velocity and this this diameter, this velocity, this density, and this viscosity, and then you keep flipping the sheet. Okay, tuck, 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 tuck. Okay, this sheet. Okay, that would be the result. That would be the drag force. That's not very smart. Not smart to conduct the experiment, and not smart to represent the results. Yeah, but another student, the supervisor gave him the same experiment. Yeah, okay, and then that student, after 1 week or like a couple of weeks, he just came with just one figure, not 450 of them, that have the relationship between like your drag force and all like these different parameter. Yeah. So here's that's like your drag force, and that's all like this different parameter. So like your supervisor will tell him, okay, now I want to change this fluid, not even use water. I want to use oil. It will tell him it is here. Yeah, you have it here and here. Yeah. Well, I want to change the column. Yeah, it is here. I want to change the velocity. It is here. Yeah, it is here. Yeah. So it's just one experiment. Not one experiment, like he did like few of them, like to get this curve, to get like this relationship. But the result is just represented in one graph, and he called like this guy, this term, he called it like drag coefficient, and he called like this guy here, like for example, like we give it like this is this guy. So this is called like drag coefficient, and this is called Reynolds number. These ones, like this drag coefficient and these Reynolds numbers, these are called dimensionless parameters. Yep. So these are called dimensionless parameter because he was able to find like this two dimensionless parameter. He was able to reduce all these. How many variables do we have? Remember, like we have like drag coefficient. That's like a function of diameters. That's a function of velocities. That's a function of this guy. That's a function of this guy. So he was able to reduce like 5 variables, like 1, 2, 3. Like he was able to reduce 5 variables to only two of them, two dimensionless parameter. How did he do this? Well, and how did he find these guys? Like how did he know that about this guy? Like how did he know that this dimensionless parameter is like this, and this dimensionless parameter is like this, and this dimensionless parameter can represent this? So how did he find this one? How did he find this one? And how did he know that this one and these two can just like represent this like relationship? Well, he knew this because he studied dimensionless analysis and he studied pi theorem. So next class or next video, I will show you how to use pi theorem to start from here, like what from this relationship to end up to here, like to get like these two or three or whatever. Like so basically here we have two dimensionless parameters because we have 5 variables. If we have 6 variables, that would be like 3 of them. So you'll get like 1, 2, and 3 dimensionless parameter. If we have like 7 variable, you will have like 4 of them. But still, 4 dimensionless parameter is better than 7 variables because we have seen that already. Like if you have only these 5 variables, and you need hundreds of experiments to understand the relationship between these guys. Okay, so next class I will show you like how to use pi theorem to find like this guy, and the third part, like video number 3, I will show you like how to use pi theorem to scale back from like your prototype, what you did in the lab, to your from your physical model, what you did in the lab, to your prototype, like your actual system. Okay, so wait for the next video.